we started this work with a vision where in the future, computing and physical world is going to be fully intertwined, right? And therefore, security and safety is very important. So it's easy to say what security and safety is important, but what exactly does that mean, right? So we start looking into unique aspects of cyber-physical systems. And from our experiences, there are two foundational differences. The first one is you can almost think about every single cyber-physical system as a cyber-physical control loop. So that is the basic abstraction of cyber-physical control systems. So you have computing in the middle, and that computing has to be done in real time. And one common misperception of real-time computing is that it has to be done as soon as possible. As a matter of fact, when everything is driven to its fastest form, it's not always the best for computing for physical controls. Therefore, oftentimes for real computing, we're aiming for predictability rather than as soon as possible. And we start looking into problems when timing is not predictable. As you can see from these experiments, it either run into pedestrians, drops a cargo, or the robotic or the humanoid falls to the floor. So what went wrong, right? Real-time systems has been out there for decades. And we have a solid theory for how to handle those, starting with if you have a task, you want to understand what is its worst case execution time. It turns out that this is actually quite difficult. Once you know, even if you get past that hurdle and of knowing what the worst case execution time is, you need to come up with the task model, and then you need to work with someone from real-time schedulability theory and say, hey, I have this task model, I know its behavior, can you come up with a scheduling algorithm for me such that I know my task would always finish? After several years working in this domain, I still feel that I don't know a lot in schedulability theory because it requires very strong expertise to get it working. This is no surprising. Actually, as a matter of fact, people went around and asked all the industry partners, how are you building your real-time systems? It turns out most of the actual robots or cyber-physical systems running out there just run testing, right? Instead of leveraging real-time theory. And practical challenges include worst-case execution time is not always available. Real-time task model is hard to get. What should be a real-time task, right? Should it be a Linux process? Or how do we break it apart? Oftentimes, you have Linux process sending messages that triggers other tasks, right? And if you just order that Linux process as a real-time task, it doesn't always work because you will need a clean completion of a real-time task. So with that in mind, we said, geez, we need to address this. We have beautiful real-time theory on the one hand, and we have messy code on the other hand. So we went ahead and did a survey study of real-world timing bugs in 7 open source projects. We select those projects because we believe they are widely used and well-maintained. Our selection criteria are we want to have different components in CPS systems, so that include perception, location, planning, control. We use different keywords to search for them to find those 189 timing bugs. And if you want to know more detail, we have the entire gigantic table that's created by my student available, and you can take a look. So to sum up, the current practice in developing timing constraint is only 9% is verified using real-time theory. And oftentimes, most of the bug fixes that we found use an ad hoc timestamp tracking. In other words, developer insert a check here and say, hey, when was this sensor data read? Is this fresh enough for me? Was this recorded 15 microseconds ago? If so, I can go ahead and proceed to my control. Otherwise, I need to do something else, right? Abort or raise an alert or lock the system. So coming back to how developer is trying to tame the timing beast, they oftentimes need to ask several key questions. What type of timing behavior I need to check? Is it freshness, or is it synchronization, or is it stable enough, right? So entire program is gigantic. I used to work on very large CPS systems, and we have million lines of code. Which line should you check? And when you check it, what is your tolerable range of domain that you want to raise the alert and say, something went wrong, this LiDAR input is no longer valid. And once you have the constraint, then you can say, I detect a violation. But then what do we do after we detect a violation? So all these are important questions that people are doing in an ad hoc manner right now. So in order for us to think about how to address this challenge, one of the things that we have to do is we need to ask, what are the key abstracted properties that one needs to check? And we abstract that into 3 key properties that covers all the bugs that we found. Most of the bugs, because some of the bugs are implementation bugs. It's not about timing. The first one is freshness, that ensures that your physical world time and the cyber time is as close as possible. The next one is consistency. So if you have sensor input, 2 data flows from 2 sensor inputs, these 2 should reflect consistent physical world perception, right? So if you have LiDAR from 5 seconds ago and IMU from 1 second ago, they tell you a different story, and this different story is often very harmful, as you can see from our previous study. And the last one is stability. That means, is your control predictable, right? And that turns out to be very important, because for many control theory, that is how they make this assumption that you get to execute this time the cyber physical control loop in a timely manner, in a predictable manner. Now, from a different perspective of fixing the bugs, we find out that many of the bug fixes actually requires bridging this semantic gap between different scheduling entities in order to be efficient. Inspired by this bug study, we come up with our solution, which is called Kairos, which aims to do 2 things. First, represent the timing expectation in a manner that is easier to use by developer. And the second one is mitigate the timing mitigate the timing violation in a manner that's more efficient. So based on the observation that most of the cyber physical control loops are driven by data, we add the temporal dimension into data flow, which we call the TAM data flow. Sorry for not being creative. Each vertex is a statement, and each edge is a data flow with a timestamp. So you would have propagation of timestamp as your data flow through the cyber physical control loop. And then at each statement, when the data is consumed, that's when you start checking for whether the time range is within your expectation or not. And we understand that actually creating this temporal data flow diagram is actually quite hard. So besides providing the API to instrument the program, we also provide tools to visualize and follow through the diagram, and we also have the profile-based testing for testing what the valid range is. One of the key challenges in profile-based testing is you can always dynamically instrument any program, right? But you need a bug oracle to tell you whether this timing violation is actually harmful and need to be addressed or not. To address that problem, we leverage the control state deviation because that tells you physical safety. So our profiling-based method is actually key on the observation of control safety. And just a quick run through of the workflow. You annotate the program with timing constraint, or you automatically annotate it with profile base. I have to tell you, our profile base is not working very well. You can use it to profile the range, but for profiling which instruction to instrument, that's really hard. Once you have annotation, you construct the graph, and then our tool will take care of the LLM instrumentation and adds all the time checking for you. And you have a DFA enable executable. Now, once you have the DFA enable executable, you would have the capability to detect timing violations. The next step is to mitigate the timing violation. What we did is, because based on the bug report, we observed that it's often necessary to bridge the semantic gap among different abstraction layers. So we create an association which we call path that links all the scheduling layer of a particular task when it's spawned. And then next, when you run the system, the instrumentation takes care of the timestamp recording and the timestamp checking. Upon statements or vertexes where you enforce the timing checking, it will check for several timing properties. In this case, it's inconsistency. Once you detect inconsistency, you send it to the handler. We have several default handling policy: abort, skip next, and prioritize. And if you think more deeply, you'll probably ask the question, wait, you can't just prioritize things just because you missed the timing violation. So when we designed this, we find out this is actually a really hard problem. And we try to leverage the mixed criticality scheduling theory so that we switch to a different profile when we prioritize. However, later on, when we conclude the talk, I would also mention that this remains an open problem for us. So once you have the scheduling decision, you want to propagate the entire scheduling decision across the different layers in the OS. We evaluated our system using 3 types of platform. Those 3 platforms are selected because they have different real-time behavior and different number of sensors, different requirement on the processing power. And we have 3 evaluation questions. The first one is, are we able to fix real-world bugs? The second one is, what's the cost, computational cost of the system? And the last one is, how much can we improve the overall control safety when our system is employed? The first question, so on the bar chart, you can see probably more than half, about 60 to 70% of the bugs is fixable using our system. The rest of the bugs that are not fixable, including algorithm bugs, hardware-related bugs, concurrency bugs. And on the right, if you believe me, that's the with and without fixed comparison. The red one is when without our system, there's big fluctuation in the control deviation. Next, we evaluate the overall system overhead. We find out that our system overhead is generally quite small under different CPU loads. And then we try to look at our safety improvement under different CPU loads as well. We observe that we generally reduce control deviation by 74% and the number of collision by 62%. Clearly, we run all this testing using the default scenario. I think if you work on CPS, you would know if you want to run it under different physical scenario, you would stretch the system in different way. And that is one of the things that we need to do in the future. So just to conclude my talk, we introduced the concept of data flow availability, which builds on top of the observation that there should be timely data flow across the entire cyber physical control loop. We introduced Kairos, which is a proof of concept cross-layer scheduling mitigation framework that is able to coordinate scheduling decisions across different abstraction layers. However, making the connection between the rich real-time scheduling theory towards a practical implementation that mitigate timing bug in a usable manner remains an open question, and we are hoping that this is a first step. And we open source our code, and you can scan the QR code for the project website. And with that, I will take questions.